Okay, welcome everyone to today's live science live stream. And today we're going to be talking about particle physics and computation featuring Nick. So Nick, yeah, please kick us off. There's going to be some exploratory things to discuss and discover. And the idea is it's not so much a presentation as it is just performing science in real time. So yeah, let's have some interesting discussions here.
Yeah, so it's not like I've prepared some presentation. I just wanted to discuss some of the things I've been like reading recently or rereading it again and maybe even implementing it in the Wolfram language as usual, right? Basically, I don't know, the best thing to kick it off is maybe just to focus on this paper, which I've shared on the Discord channel already,
Okay.
right? Which is like this Rosetta Stone, the common language one has to, the existing for at least four fundamental things in science, right? Physics, topology, logic, and computation, right? So we were basically being focused on all of them to some degree, right? Physics, obviously, topology, maybe you can kind of uh, relate it to all the infogeometry stuff somehow.
Yeah.
Logic, also paid attention to with all of the automatic field proving and mathematics, and obviously computation as the whole grail for under all of this, right?
Yeah.
And this is basically this paper describes all of this and the common language under category theory, right? What kind of categorical language unifies all of these concepts, the concepts in all of these four fields, right? And it's like basically making diagrams. Let me find actually some table. There's some maybe at the end of it is like the most complete one. I don't remember where. That lists all of the terms in all of those four fields so that we can relate them. Yeah, in the conclusion, right? So we
Very
have
cool.
this.
Can we zoom in like
Uh,
a couple notches on that? I just want to see the yes.
yeah.
Okay, great. Okay.
Okay. So what do we have? Right. So usually like physics, basically this left column is the category theory language, and
Hmm.
the other four columns are the usual things, how you describe things in all other fields. Like in physics, you deal with Hilbert spaces, so it's mostly about quantum physics, not like general relativity. But general relativity, you can think of it as maybe this topology, the topology columns to some degree, right?
Okay.
So, and it's all about like some kind of objects and morphisms. So basically, arrows from object to objects in the category theory, right? So we have
What is a
morphisms and
cobordism?
operators. Cobordism, well, in topology, is just a manifold of degree of one dimension higher than the manifold itself. So it's like a way to map from one manifold to another. And also it's like you
Okay.
kind of stretch it in time. So if you have like one space, another space, the cobordism is whatever is in between. So it's one
Hmm.
plus one dimensional manifold again. So space, time. So
Wow.
cobordism is like a space time. So that's why I say it's like a general relativity
Hmm.
basically. A proof is like a way of going from one proposition to another, and the program essentially, or function or rule, is just in general how to do computation from one type to another type. So it's basically more computation with types, not just general
Hmm.
computation.
Hmm.
And you can the tensor product is just a part when you starting creating category in category theory monoidal categories. So you have a monoid, which is basically the way to stack two objects together in a different way than morphism. Like this is just like composing objects together vertically, like one after another. You should think of it like vertical as space, as time. This is like stacking them in space, so side by side, horizontally, right? And I maybe like in addition to this table, I was kind of thinking of maybe showing off some of the things I've been developing recently in terms of trying to make a package to make these diagrams and all these category related things in the most abstract sense,
Hmm.
codable for language. So we can make diagrams like this,
Very
right?
cool.
But not relating them directly to any of the like concrete categories like physics, topology, logic, and so on, but just making diagrams themselves. So it's basically like a, well, in a sense, it's just another concrete category. You can call them concrete category of diagrams, Wolfram language diagrams, maybe, right? It's like similarly how like Haskell people create their own category like called Hask, right? Which is just basically the computation with types category, but it's more concrete because it's implemented in language, right? But it's still like just one another thing to describe the same thing. So but in a way, instead of using category theoretic language like objects and morphisms, you just build diagrams with arrows and compose them together. So basically, we can make. I just want to show off. Maybe I'll make this one even larger, right? So in a way, all these categorical abstractions, we can like a composition and tensor product, and even like all other things, to some degree, can be represented as just diagrammatically as string diagrams, where the most basic object is just this piece of morphism, right? And this is like, or even maybe I'm skipping a little bit. So maybe there's like should be how do we describe before going into morphism, how to describe objects. Basically, this is like builds on idea of graphs with ports. So instead of having some just objects like this, you just have some ports, right? Which is just some basic things. Just you can create them. They have some complicated input form that you don't have to worry about. And there's some built-in algebra, like you can make products of them. You can make sums, which is just why, which is that monoidal character of those objects, right? You can stack them together. You can sum them together and all that. Just they have some algebra under the hood for how you manipulate ports. You can also
So you have to
take
do the
tools.
algebra inside of it. You can't do port A plus symbol port B, like as a
Well,
separate
I
thing.
haven't made them like this because ports are not important for on their own. Not very important. It's just like you can think of this because we're just making
Abstraction.
diagrams, string diagrams, just wires. So we're
I got
creating
it.
wires, right? So but you're not allowed to like touch them individually just as wires.
I
It's not
see. I
very
see.
interesting, right? So
Yes, yes.
the interesting part is when you just create diagrams with ports. Like this is like automatically makes a port X as an input port, and then port Y as an output port. So in a way they're already different because this is like the ingoing arrow, the ingoing wire, and Y is like outgoing wire. So it's like a convention. It's just where you create a diagram. Like, oh, this is like a more complicated examples. Multiple inputs, multiple outputs. And if you like copy it, you by default this is like a port, which is dual, and the dual port it basically tells you which direction of the arrow. What is the direction of the arrow? If it's ingoing to the diagram, it's like a dual. So by default we have this notion of directionality of each arrow, and that's where
Why using the term dual? What does duality have to do with it?
well, if you just focus on just pictures, you can think of it as just the direction of an arrow. But if you go back to all the categories, right, it actually relates to like maybe in this picture it's not obvious. It doesn't have duals.
Yeah, that's why I'm asking. I'm
But the
not sure.
arrow directions is there, so it corresponds to the way to have like as soon as you have diagrams and categories, the dual actually means whether you have like a reversing old arrow, so it basically corresponds to going into opposite category and things like that, right?
That's a category theory term. It's like a term from category theory.
In a way, yes. So
The syntax you're using there.
yeah, maybe it's a. I actually wasn't sure how to name it in this context. Maybe duo is maybe very confusing. It could have been just a reverse port, right? Because I was going to not use categorical language at all, or use it less, like
That would be
as less
great.
as possible.
Yeah.
Yeah. So it's like making. That's why it's just I actually never type duo. We just make it a star. So
Star.
no, it's
Okay,
just a
star.
super.
I like star. That sounds good. Okay.
Right? So you don't have to actually. There is a duo, right? This is just a maybe not. You don't even. It's not even allowed like that. duo of the arrow. This is just reverses. Duo of the duo is it's like a
Okay.
go back to itself, right? So it's like a
So it's
how the
reversible, something like that. Like that's the point.
yeah.
Maybe. Okay. Okay.
Now, is the diagram function calling the port function under the hood?
Yeah. So it basically wraps all of this, and by convention, that's why we call this inputs, and we call this outputs. Basically, all the inputs are calling the dual, so they all reverse. By default, outputs are outgoing, so they're as you ports as you give them, so they don't have start.
Oh, I see. Okay, so a port can be either ingoing or outgoing. So depending on the order in which they're called in that function, it's going to diagrammatically be inputs or outputs.
Yeah, exactly.
Got it. Okay.
Or it's like it's basically the convention that there are two of them, two sets of them. First set is just being dual, right?
Hmm.
And there's actually more complication to it. So there's some notion that I've been exploring how to design is like the idea of neutral ports, and maybe I won't go into those.
So
Those are unrelated.
if in
Yeah.
one input, if you replace small a by a star, does it change the direction of the arrow or not?
Yes.
Okay.
You reverse this. Yeah, exactly.
So does that now become an output or does that become a reversed input?
Well, that's why these two sets are kind of conventionally called input and outputs because they just drawn on top and the bottom of the diagram. But you really have to look at the diagram or just the directionality of the arrow, not the position.
Okay.
Where the arrows, because you can even like when I showed it, you can customize the graphics. Very like in detail, you can put arrows in a different position. Like here, I'm placing the X, the first arrow, on the left of it, and I also change the shape and rotate it, all that, right? So in a way, the place, the node itself, this morphism, this object, the morphism and the objects can be pointing from all other directions. So you basically only care about the directionality, whether it's ingoing, outgoing, right? And how you compose them together. There's like another interesting thing that you can basically treat the morphism itself as at least diagrammatically, as a wire itself. So it's just like change the shape to a wire, and now you can start composing them. You stop, like you can make this diagram, right? Now you can, if you don't show this outline over here, you start like making this weird shape. But even though the under the hood diagrams are composed together, so you're basically dealing it with algebraic object, not just as two pieces together on a canvas. When you just created your wire itself, you actually have a composition of the hood. So it's like just heavily customized with the positions and where the things are and how styled
So
they are.
that could be something like a type and a subtype, and they kind of like they can be connected in a way where it doesn't really matter because a subtype of a type isn't a problem. Something like that.
What do you mean subtype here?
Like X could be mammals and then Y could be sheep. And then like you can flow from mammals into like as an input port through sheep, and it like doesn't matter because it just
this is like maybe the fact that I'm changing the type here, it's maybe not allowed if you really treated this particular node, this diagram as an actual identity. Maybe you're not allowed to change it. But if you don't care about semantics, what actually this particular diagram represents, like maybe some Feynman diagram, that's where we're actually going into, right? If you want to represent physics or you want to represent computation, and this is like an identity function that doesn't allow to change the type, then maybe this is not allowed. But because you don't have to, you don't like impose any semantics for now on these diagrams. We're just dealing with things that can be composed. So it's even in a way, it's even more general than category, right? And all those categorical semantics. We just
we're not dealing with constraints yet. This is the constraintless.
We artificially remove
the tool set. Yeah.
Even though actually the ports are the same, otherwise they wouldn't Like at least the port, the actual ingoing port into this B diagram and the outgoing ports should be the same. Otherwise, they wouldn't compose. So that's like the only constraint here. But the fact that we changed the shape here, like there's no diagram at all, just an identity, then maybe that's a little bit cheating, right? Though this is just
So,
just a visual distinction.
diagram composition is a new diagram, so it's automatically associative, your diagram composition.
Well, associative, like association. Well, there's no association, right? It's just but it's a new diagram. Yeah, this like
Yeah,
this
so
logic.
but if you compose A with B and then compose the composition with C, then it's the same as if you compose B with C and then you compose it with A at the beginning.
Well, if there were any way to actually compare them properly, then yes. And actually, yes, the way I've done it, diagram composition is associative, so it's kind of if you compose composition with another diagram, it kind of puts it inside composition. So it's like it assumes that diagram composition is associative, yes. Though it's like you can like basically make. I think I'm gonna skip this for now. But in addition to like this composition, which is like vertical way, which treats the ports, tries to merge the ports together when you compose them, right, vertically. The diagram product is that an exact thing. The monoidal product is the way to stack two diagrams together in space. So there's no wires getting merged, right? This is in the table that we were just looking into. Oops. Right, it's just the product of two diagrams, or the product or the tensor product of tensors, or just parallel composition of two functions, or just two wires going side by side, or like the tangles, whatever. Just the monoidal structure of the category means that you have to stack those things together side by side, right? So you have at least two ways to compose diagrams together. That's another way. Right, the diagram composition is just vertical compositions, so it takes into account the actual wires. If I this is like you have to read it from bottom to top because it's a composition, right? But for actually, let me try to change it, break it for a sec, and see what's gonna happen. Oh my god, it's so small. Right, if I change the B so that they no longer compose, they just stack together automatically side by side. Right. So it's like that. Basically, it knows about the ports. There is also a sum.
So what's the difference between this and association? Wait, it's the same diagram composition that you had above, right? When you just connected the ports. It's the same function. Okay.
It's the same function, yes. So
Okay,
just
okay.
you feel it's like a function. You think of it as a function composition or dot product. If you think about it
Okay.
like matrices, like this is like a row, this is like a column, and the wire means to contract them together. So you either think of this as sequential composition of functions, or dot product of matrices, or just like wires stacked together. And the port just tells you whether do you merge them together or not. So there's some mechanisms going on under the hood to decide actually whether the ports are the same or not. In addition,
So if you have something like a matrix that has a dot product when they can't be merged, is that because maybe the dimensions are different or something like that? There's some kind of constraint where
in a way, this like ports in when you semantically interpret this diagram as a matrix composition, like you have matrix A, for example, maybe it's 2 by 3, right? And matrix B, which is like 2 by 3 by 2, right? So in
they work,
that, so you can compose it because now you can dot products with this 2 dimension.
That's really cool.
Okay, so this is like a little bit unnatural because in the way you specify it, not like you specify inputs first, outputs second. So, but when you list dimensions of the matrix or a tensor, you usually go from outputs to inputs. If you usually you compose it in a standard way from left to right. Right? That's why we have in addition to this diagram composition, I have a column diagram, with now, where now you can, well, you have to put them in a list now because you think of it as instead of a composition, you're just making a column, right? So in a way that's more natural. So you're composing these things together. So now you can see that this 2 is next to this 2, or maybe it's a little bit more natural.
And then what happens if they don't match? Do they also go side?
If they don't match, they're just gonna make them side by
Okay.
side. So
Okay.
it makes a block. Right. So the sum is maybe it's not important. It's just like another completely different monoidal structure you can impose on the diagrams. Instead of taking products, you can also take sums, right? And and if you have both, you have bimonoidal categories and so on. But it's like I don't have. Well, I haven't thought about how to treat sums a lot. But it's like, for example, you can take this. In a way, you can even having this bimonoidal structure now. In general, you basically maybe you have to create 3D diagrams now because you now can stack two diagrams together in space in two dimensions, right? So that in order to distinguish them, so you have this product, right, which is like a multiplication of two diagrams together as a pair, and also have a sum, right? So maybe in order to distinguish them, and also you can do the same thing for ports. You maybe do the stacking into different dimensions, and you have a 3D diagram instead. Maybe that's for future to actually make 3D diagrams, so that you can distinguish those two different monoids better, right? But the more important thing is actually there's more interesting way of composing these diagrams instead of actually making them as a grid, of making them of composing them vertically, horizontally. You just you use this sort of list all the diagrams and turn them into a network. So it's like a very similar to how you do like Penrose tensor notation or Einstein summation of indices, when you just list all the tensors and indices and you assume that by convention you sum over all identical indices, right? So that's like so here is basically the same idea. You just list all the tensors, or in this case just these diagrams, and you assume that all the same ports gonna be smooshed together somehow, right? And create this, if there are more than 2, there's gonna be like this extra vertex created. So it's like a called spider in some literature. If you deal with Z calculus and all that in tensor notation, it's like you're creating a spider. But if there's just, let me change this so that there are just 2 things. Yeah, you can customize them. That's why binary spiders, you don't have to create them. They're called spiders, which is a weird name, but you don't, if you there's just 2 ports got merged together, you don't have to create an actual vertex. So now it's a graph with one edge, right? And this would be treated as a hyper edge. So in a way you can smoosh those diagrams together by very general port merging like this. Right?
That's very cool. So it's kind of like you can take the concept of you can construct any type of hypergraph just with combinations of like bidirection with combinations of directional graphs in this diagram kind of flow.
Yeah, in a way you can, in a way these diagrams have a corresponding hypergraphs, and also like this package for diagrams can be also used to interpret all other objects like quantum circuits, graphs, hypergraphs, trees, system models, when it's actually already like a diagram, as a purely abstract diagrams like this. So
very cool.
You should be able to turn them back and forth between them.
So there's one thing I wanted to ask about that specific diagram you had there with the spider. So in the middle, there's like the B spider or the A spider, sorry. And like all the arrows are inputs to those ABC boxes. But can one of the arrows for the A spider be flipped into the other direction?
Here I flipped it. So now this A is an output of B.
Oh, there we go. Okay. Yeah.
Right.
So it's a completely generic way to add direction in any possible combination for a hyper edge.
Yeah. Even if you like create this diagram and so on, like AA, right? It's just
Hmm.
input and output is A. But as soon as you,
Okay.
as soon
Wow.
as you,
Yeah.
when you make it as a network, you have to make a loop.
Yeah. Yeah. So it's a unary hyper edge, or no, it's just a unary edge, right? Yeah. Is that the right word? Yeah.
It's a, no, it's not
It's
unary.
an
It's
edge on
still a
its
binary edge. It's just a loop. It just goes from vertex to itself. It's a binary edge. It's a
yeah.
binary.
Yeah. Yeah.
So it's just a
That's
graph. It's essentially like a graph with a single edge like this.
yes. Yeah. Yeah.
Yeah.
It's very cool.
And the cool thing, you can actually go back from this diagram, network representation and grid representation, which is just stack together nodes vertically and horizontally. All you have
But
to
what
do
I
is
like,
arrange it.
yeah.
And it's like now it's like a grid representation when there's a special diagrams were inserted. You see, there's like a kind of this is
Yeah.
actually let's make them this create this outline, or maybe hold on.
So you can turn it into like Lego pieces where you can like pull the stuff up together somehow.
Yeah. So in
That's
order to
very
see
cool.
explicitly, there's actually inserted here a new very complicated like with a lot of options in order to customize it. Basically, this
Wow,
is like
that's
a
so cool.
diagram on its own, right?
Is that how you constructed the quantum circuits with this kind of technology, or this would help
No,
if you were to do that?
they were predating this technology, but you can do the circuits with this one. So it's like
Yeah,
a
this is so cool.
much more general thing.
Yeah, and what I like about this, if you go up a little bit back to that single binary edge, is that it's more general as that arrow, yeah, where you had the single loop.
Like that.
It's more general because you're specifying the direction of the input and the output. Whereas with the current graph structure, it's only one. It's assuming the input and output is the same direction. Like if you scroll up a bit, like to this the tiny little unary edge, the unary what
Here,
output to yeah. So you see how it's like the arrow is going back into itself. So that means like the input is on that point.
Yeah.
But there's an assumption of the output being that in that direction. But the edge
Yeah, well,
could be
the assumption here is just because you're constructing graph. A graph assumes you have some explicit notion of edges, so you explicitly list all of the edges in order to construct it, right? So you have all the edges. So in the graph here, the idea with all these diagrams and compositions, what you're constructing just a morphism. So you're dealing with the category and you just list all its home set or whatever. Just the list of morphism on its own, so the list of diagrams on its own without explicitly making wires. So in a way, wires are implicit because in the way you compose those things together, right? You
they're explicit or implicit. Yeah.
They're implicit because you never create a wire. Like I never created this, right? I never like said that you have to make this wires and this diagram. So in a way, you just start composing things together because you're only specifying these nodes individually what kind of ports they have. So you only specify the ports, and then the way you stack those diagrams together give rise to all the wires, creates all the wires, right?
So
you can, yeah.
Can you also represent hypergraphs with oriented hyper edges, or you would need some cyclic order around the inputs or something like this?
Well, yeah,
I mean,
I guess
technically
like
each one of these modules is an oriented hyperedge. And oriented hyperedges, you have a list of inputs and outputs.
Yeah. It's like, yeah, it's already like this diagram, it's already an oriented hyperedge. Just maybe if you want to generalize it even further by specifying some symmetry associated to it, maybe you can just annotate it. Because this A here, it can be arbitrary expression, right? And you can stack all this information about symmetry of this hyperedge into that expression over there, right?
So you can encode your meaning onto it, like somehow.
Yeah. You can like maybe the nice way of doing it is like make an annotation A, and maybe say, okay, there's symmetry here, is blah blah blah, right?
Yeah.
And it's not gonna be shown here, but this like information is there. You can like take this, and if you extract the expression, which is this A is actually annotated A. So under the hood it's annotation. And actually this kind of annotating mechanism is very useful when we want to impose some actual semantics to these diagrams, like making tensors and functions or programs in general, or propositions if we're dealing with logic, right? All right, but maybe I'll show it later if there's time. But yeah, there's some more complicated mechanisms to actually customizing the port function. So this connecting wires works more like an actual graph creation. So in a way, you can shove all of the information about what ports to connect to into this special port function, right? You create this connection function based on the list of edges, and now even all of the ports are different, right? You just you uniquify all the ports for all the individual nodes, right? So they're different, they don't merge on its own. So you have this network, but as soon as you specify this connection function that tells you, okay, these ports are actually the same, then the merging is performed. So that's how you can make graphs and hypergraphs by if you have some actual edges, right? So this, as I already showed you, right? You can, there's some different way for composing things, right? So you can like make more complicated diagrams. You can customize them. This is like a very more complicated examples. You can basically of making a grid, right? This is like sometimes there's some permutations are gonna be inserted because the ports don't match in the ordering. So there's this extra permutation thing's gonna be inserted, which is just another diagram, which with a clever shape so that it shows that the actual wires going, even though it's just like a diagram on its own, right? So create this thing. Oh yeah. Another complication is actually you can, because this diagram is also supposed to be hierarchical. So you can have like diagram inside of diagram inside of diagram, right? So in a way you can override some ports for each of the layer of those diagrams. So if, for example, if you create this product of two diagrams, so like here you can say, okay, the actual ports not A, B, X, right? But maybe you want to swap B and X. You override the ports completely. When you're gonna do it, it's gonna recognize it that they actually don't match and show this frame around the whole thing. And your actual ports are going to be connected to the ports that you actually specified. So you can even remove them. You can, for example, you can say there's no actually out ports at all. So basically make this diagram out of those two pieces that don't expose any output ports at all. So now it's just creating these frames. This is just for making this hierarchical structure more explicit, right? You can just specify that only a single port is joined to the inner diagram. So this is a kind of this port just got orphaned, so to speak. So because we don't connect to the outer frame.
So this is completely generic. So that outer diagram, the outer square, that can also then just have arrows going out of it, right? Like from the B, you can just have an out arrow. Or how would you add that into this?
Well, this is just the inner diagram, right? So this is you have
sorry, the small b at the right at the bottom, that final output.
This one.
Yeah.
Yeah, this is just a port. Yeah. So you can put other ports. So it's in a way this outer diagram is just reassigns the port of this product of these two diagrams. But when you create the product like this, it has some ports associated to it, like IX as inputs and BY as outputs, right? But as soon as you can also overwrite it without modifying
the
internal
information.
diagram.
Okay,
Those A and B still have their original ports unmodified, but you can just reassign it. And in the way I show it is just by creating this frame around it.
So is that like a morphism between morphisms or something? I don't know.
I wouldn't say it is like it's not like a morphism between, it's not like a two category. I think that's the way you call it.
What's the thing if you have, when you have one category and then you have another, what's the thing that goes from one category to another category?
It's a natural transformation, yeah.
Transformation,
yeah.
That's not called a functor.
Functor, that's the word.
Yeah, there's also things between, yeah. Or there's two categories, three categories, and so on. Like actually, let's not go there.
Let's not go there, okay.
Yeah. So, all right. More complicated examples. This is just a way to extract subdiagrams. Like if you're given this thing, you can just extract all the subdiagrams with all the products and individual nodes.
So just zooming out a bit to touch on that concept. I mean, basically what you're doing is you're constructing a tool set that you could be able to have like category theory, physics, topology. You could like construct those things out of these very most generic kind of like fundamental building blocks, something like that.
Yeah, in a way, just deal with the string diagrams in the most general way possible. So that's kind of the goal here, because they're a very common language, becoming at least the most very common language across these disciplines.
Yeah.
Right. So that's why we want to create the framework for them, of manipulating them and constructing them. Right.
Yeah, because I mean, we talk about this stuff from a theoretical perspective a lot, and it makes sense when you kind of describe things. But if you want to represent it visually and computationally, you need to actually create these tools to be able to put these things into a notebook, and then you can start manipulating them and computationally enumerating them and doing all kinds of stuff. So the trick is to get to like, at what level of generality do you want to get to? I think that's always like the challenge with engineering. And I guess what you're doing here
is the design problem. Yeah. There's like all of these design decisions one has to go through in order to like think, okay, what is this? Like this diagram network and these frames I've showed you, those are very confusing. It's like when I first came up with it, they were very confusing. How to like just mix them together when you have these different ways of composing diagrams? How do you actually mix them together when they become this grid-like composition and network-like? When you just mix them together, what is going to happen? It's like very tricky to get it right.
Can I just ask? Sorry.
Yeah, go ahead.
I just wanted to ask, would your package, if I wanted, because in my math work, I was dealing a lot with operations with multiple linear operations with multiple inputs and multiple outputs, and I was having some partial compositions of many of these operations and so on. Is your diagrammatic framework, and actually precisely what I was drawing was diagrams like this, if I kind of wanted to consider some compositions or partial compositions, would your package somehow make it easy for me to implement such partial compositions? For instance, if I wanted to check some computation, like via some annotations, and then see it as a, and then get the actual partial composition from that.
Well, if you do by partial composition, maybe like you mean like things like this. The way the C and D compose together, you have this port just goes through it.
Yeah. Right? So if I wanted to annotate to C some function with one input and two outputs, to B some function with one input and two outputs, and to A some function with three inputs and one output, is it easy to just to translate this diagram to an actual composition?
Yeah, there's a way. It's like I said, you have, and I'm working on. Actually, maybe I can show this. You can draw this. Hold on, let me. Where is it? Yeah, tensor diagram. No, yeah, diagram function. Basically, this is like one way of imposing the semantics to a diagram. One way of actually imposing the actual computation is just imposing what would be the function. Right here, I think if you create this node, a single node with two inputs and two outputs, right? You can even annotate it with some function. So what to do with the inputs and what to do with outputs, right? So this is like corresponds to the input number 1, input number 2, and if you return a list, which means creates 2 outputs, right? So you can annotate it with this actual function. The diagram function would try to turn this diagram into an actual function. It's going to be a little bit involved. You can customize it a little bit, but the idea is that yes, this is the composition. Involved this not the composition in the diagram, because this is like just a naked node, doesn't have a composition. This is actually composing the way to morph inputs to other inputs. In a way, this is just makes a list into a sequence, so it's not very important. But when you actually have a diagram composition like here, right? Actually, let's make it's partial. Let's see what's gonna happen. So let's make this F, also make this extra C output, whatnot. That's like the problem where this frame is created to show me that the actual ports are different. I don't know. Don't worry about this. There's still different ways. So this is the composition you wanted, right? So it's a composition of F, some boilerplate to work with outputs, I guess. G, and then that's it, right? And also morph its outputs. And if you have a product, then it's also going to work to some degree. So if you have this column with a product, then this H, in a way that you can run this H and this F in parallel because they're in the list. And actually, if I think I have this option. Let's see what it actually works. No. Oh, what am I doing? Parallel. Yeah. So in a way, you can actually make them parallel. So now, as soon as you have this product of diagrams that can be run in parallel, you, by creating this function that actually has this parallel functionality built in. So it's in a way, each of those calls to F and H now are called using parallel submit. So that makes sense. But you can even generalize this even further. I've been thinking recently and reading some literature and actually how to better deal with the reversed arrows and dual ports, basically, in the computational context. So in a way, in the categorical language, this kind of semantics of functions just correspond to the closed category, which is just to say that there's some function types exist in the language, so we can turn them into functions and fit functions to other functions and so on. But if you want a more general category, when you have you can take traces and loops like this and also interpret them computationally as a function, then you have to create some additional semantics. What does it mean to have a reverse type, inverse types, negative types, fractional types? Like what does it mean to divide ports
Fractional
and
types.
subtract ports? Yeah. And there's actually there's some literature how to interpret those types of
Types.
types of ports. Yeah.
Meta
So
types.
how to interpret them?
Okay.
Actually, maybe
actually,
I have it open here. Maybe.
yeah. So that was actually going to be my question for today. So let's get into that. I'm very curious about something you mentioned when we were chatting yesterday about anti-types, and that kind of like made me start thinking very meta. So I'd love to figure this out.
Yeah. So this is like one of the papers I've been looking like I don't know, since yesterday, just for a couple of days. No, I haven't even read it fully. So, but it's like one of the ideas how to just take this most general compact categories, which compact means that you can have this inverse arrows.
Okay. Oh. It's frozen for a moment there. So, do you know what a compact type is? A compact category?
Hello.
I just know compact from topology, closed and bounded.
Okay. You're back, Nick.
Yeah. All right. So yeah, I've been saying that the compact one, the compact part of the categorical language means you have you have these loops and inverse types basically, right? And this like paper is just one way of interpreting those inverse types as an actual computation, as an operation that one can run. So it's like describes this machine, universal reversible machine with these inverse types. So maybe my next goal gonna be actually implemented in the Wolfram language. I think would be cool. So that
That's
as soon as they
crazy.
implement this Pi machine with all of this additional semantics of inverse types in the Wolfram language, for example, so that you can run, then I can make an alternative to this function semantics that just has this composition and maybe parallel submission of diagram port, like a product of diagrams. Now you can turn arbitrary diagram to this Pi machine and then run it. And
So what's the Pi machine?
Well, that's what this paper is describing. Or at least
It's
maybe
like a theoretical machine.
Yeah, it's just no, they actually have the implementation in Agda. It's just like what kind of language? It's a language basically, right? So it's what kind of types it contains, what kind of values, all of the things, and then there's some basic machine which is just Pi, but then you can enhance it by introducing all of these extra things like inverse types into it. And at the end, you can enhance it like you add negative types, then inverse types, like fractional types. And
That's
at
an
the end,
inverse. It's not an anti. So it's not like null and not null, as an example. It would be like, yeah, maybe.
well, it's like I said, there's like two monoids you can make. There are two ways of stacking two diagrams together, either horizontally, either with a product or as a sum. And for product and the sum, you have usually 2 units. Like for the integers, you can, if you have 0 and 1. So in a way, you can have a 0 port and a unit port. The 0 acts as a unit for summation. If you add it to another port, it doesn't change. And a unit port acts as a unit for multiplication, and you multiply it by port, it doesn't change it, right? So you have these two monoidal structures, one natural ones, and for those of those you can make an inverses. So that's why I have a negative and inverse ones. Negative are the inverse for this additive monoid. So the way you, because it's like a minus sign, and inverse is like this inverse for the multiplicative monoid, because that's like basically how you divide ports, right? So it's like 1 minus or 1 over something.
But you couldn't get a -0.
Well, 0 is you can't even have 0, not just 0. In a way, 0 is just like for example, if you want to have function semantics, 0 means a type with no inhabitants. So no, you can't even create it, right? So you can describe it diagrammatically, maybe draw some diagrams, but because there's no way to inhabit the 0 type, you can't really turn it into a computation or anything.
It's like a null or something, like the null type, maybe.
In a way, well, in different languages, it's called different things. Maybe void.
Yeah. Void.
Yeah. In a way, void actually is not a 0 type. It's a unit type. Confusingly, I think void usually means something that's just inhabited with a single element. So it's just like, but so you can create it.
I see. You can work with it. Yeah.
It's like, I think like in Haskell, just like this unit type.
Okay.
Which is like of the same type. So it's like a unit type and a single inhabitant, also brackets, parentheses. So you can make this value of this type, and you can make functions.
No, it's like in JavaScript, you can work with a null, but you sometimes can't work with an undefined. Something like that, maybe. But undefined is sort of like a type, is it? No, it's not. I don't know.
So those are extra semantics. But if you just deal with this monoids, you just have to think about what the 0 type is and the unit type is, right? That's basically
very interesting. And then there was a very interesting comment you made recently, and this might be related more on like the physics side, but you're talking about like a particle and an antiparticle as maybe some correspondence to a type and an antitype. And then there's like a
In a way,
time
yeah.
reversibility connection to that.
If you start interpreting these diagrams, now not just purely physical in a sense of quantum information, it's just like gates composed together, but more like a quantum field theoretically, when you just have interactions, and now you interpret these wires as particles, then yeah, you can totally have this physical semantics of drawing Feynman diagrams and interpreting these diagrams as Feynman diagrams. So now you have propagators and interactions, and you can try to figure out what this loops means, why they have this negative factors corresponding to them, like a fermionic loop being -1. Why can it destructively interfere with the bosonic loop and things like that? You have this nice physical, nice semantics for underlying quantum field theory too.
Very cool.
And my hope is just like also while my immediate goals is to first implement this pi machine with all these inverse types. But the thing I don't like about it is that they try to make it deterministic by actually imposing that, okay, these loops of the certain type and all that, but they also have a comment about it that maybe the natural way of when you have this, for example, maybe I have a quantum circuit. As soon as you have this, I guess this U-turn, right? This diagram, which is just creates two things, which is just a pair creation, right? Particle, antiparticle from vacuum. Because on its own, it's unclear what kind of type this wires has, because you create them from nothing. Those can be multiple type. In the quantum information world, this is just a Bell state, so it's kind of superposition or entangled pair of particles. So in a way, instead of making some arbitrary deterministic semantics of assigning some certain types to all different U-turns you can create, actually make it non-deterministic, so that you can now have a ensemble of these pi machines that you can run, and you then interpret it as even though each individual one you just like one sample from the quantum circuit directly. So in a way, each pi machine run simulation corresponds to just one sample, and when you just simulate an ensemble of those, can you basically interpret all of this backtracking in the semantics of it with inverse types, and you recover all the quantum probabilities out of it when you just start sampling like this. So in a way, you implement this retrocausality and all this backtracking necessary for interpreting quantum computation directly as this pi machine. Can you also mimic all the quantum features? So that's the goal. I think that's going to be great if that works. So start with this pi machine with this weird types, and also actually add non-determinism in some way.
You want non-determinism so that you can simulate quantum phenomena.
Yeah.
Maybe the pi machine is deterministic. That's what you're saying. Does that mean okay, does that mean that what does it mean to be deterministic? That's not the same as like it doesn't halt, right? It still has the halting problem. But what does determinism mean in this context?
Well, in this context, is usually like only all the non-determinism happening in this kind of U-turns when you create two particles from the vacuum, right? Or just create this pair.
Talking about like from a physics perspective, the determinism, or computationally. Like computationally, I mean, what does it mean for a system to be non-deterministic?
Well, in this case, we don't make this
not a
choice.
Definite answer.
We don't assign the type. We don't assign the type to this U-turn beforehand, because that's what they put in the paper.
Saying, like, which one is the particle, which one is the antiparticle?
No, it's like just what particle it is. Basically, you say, okay, this is electron with a spin up, right? And nothing else can happen.
Is that like having a function with an if statement in the function, and then it depends on what some input is or some external variable is? It's like not stateless. There's like some state or something. Maybe it's a function every time you run it, it changes or flips in some random way. Does that make it
There's a
non-deterministic?
state because it's like a classical machine. There's some kind of state associated to it that is getting modified because you can actually run it, right? You have to somehow implement all the backtracking and going backwards in time, so to speak, right? But you still have to interpret it. Sorry. Anyway, there's not. So in a way, you can still have this computational time that it should implement all the backtracking, right? So all the events corresponding to the backwards moving events still form the space-time in the usual sense.
Is it kind of like, okay, if we think about it just like a function in a computer, it's kind of like you have inputs, it gets processed in some way, and there's some mutable states that might be external to the function itself. So you might have like what's it called? What's it called when you have things that leak like information? Yeah, it causes like problems when you have like mutable states. But anyway, the point is you have inputs to the function, then you have like some outputs. But maybe if it's reversible, do you mean like you can take the output and then put it into like the back of the function, and then it can give you back the inputs, something like that?
Yeah. The feature of this pi machine is that it is reversible. And one of the reasons it is reversible because it fundamentally deals with linear types and all that. So in a way, it treats the thing, the values associated to types very seriously because there is no cloning or distraction of deletion of information happening because of the linearity of types. So there is no way. So it's already, the computation itself already acts and has this quantum features built in by the nature of linear types. So as soon as you have this linear type theory, and you also augment it with these special types, and with having this backtracking and backward computation, I think it's basically going to be semantically, at least categorically equivalent to the quantum computation, right? Even though it's a classical one, and you can treat it like so. So it's just, I think that what it lacks is this explicit non-determinism, which is kind of interesting to explore, to make it non-deterministic pi machine.
Yeah, I'd love to explore it next time as well. I need to go right now, but yeah, maybe you can take some questions and from the chat, and we'll catch you in the next one. Okay.
See you, James.
Yeah, so questions from chat. Mano Diaz asks, we can graph polystrings and Hamiltonians and then have a backtracking data, which is accurate?
I'm not sure about, well, if you, no, I'm not sure I understand the question. You can have like, if you make a Hamiltonian and you simulate it in the usual conventional like tensor network way, or maybe you trotterized your Hamiltonian into actual quantum computational circuit. You can run it because it's a circuit, it's like unitary, you can run it backward. Maybe that's what it means. So, but I'm not sure what the question is about backtracking data, backtracking data. Are there any other questions? Yeah.
So all these diagrams, it's not like pushing values through these and computing functions, or is it? I mean, is that what you were talking about with all that function on discussion?
But without diagrams, they're completely blind to the data that you store in the expression, right? A, B, C. Those can be arbitrary expressions. But yeah, the semantics, when you have like annotate this function, that function, that's only used when you have like some extra interpretation functions. Like this diagram function tries to interpret diagram as a function, right? That's why it's called that. That's where this annotation is used. But by itself, diagram is just like a string diagram, nothing else. And you can make, instead of a diagram, like you can have a tensor diagram, which is also tries to attach some semantics to the diagram, but not as a function, but as a tensor. Like here, you can make a composition you can actually go back and forth. There's like a diagram tensor and tensor diagram. And actually, tensor diagram, diagram tensor is if you have this diagram, you can interpret as a tensor, just like a matrix symbol. You can flip it. I actually haven't showed you what flip means. There's some unary operations you can do on the diagrams, but basically those are like correspond to transpositions of diagrams. Reverse it, conjugate it. You can, if you make a column like this and interpret as a tensor, obviously it's going to be like just a dot product. So this is like just a dot product of symbols.
Right.
Or
The
if-
dot product is contracting the last dimension on this one and the first dimension on the next one.
Yes. Yeah. And if you have this network composition, when you don't have this grid-like structure, then it's going to be by default interpreted as a tensor contract. So basically, slap all of those nodes together as a product and then contract some of the ports together as a tensor contraction. And if you try to arrange it, like this is just this diagram. If you arrange it into a grid, which are automatically gonna be, then this as a tensor is gonna be a dot product, I guess. Right. This is just different ways of making tensor expressions of the diagrams.
Okay, so can we get like a non-dot product tensor operation?
I think like here it's a Kronecker product. So this one, right? There's no composition, but let's try to make. If I do this, right? That's more interesting. It's like so this would, as a tensor,
Yeah, so that's C dot B.
contain
Kronecker
So
product
this is
A.
like a dot product, and this is a tensor product, and also some transposition happening. So it's B composed with C and A. I'm not sure about that, why the transposition is here. It's not obvious. Okay. Oh, never mind. This like functionality is not perfect yet. Still things to debug.
I was wondering if, sorry if I missed this, but is there a way to interact with these graphically? Like, and do you think that would be useful?
Well, there's one way you can. I haven't showed it. Just there's like this diagram draw, for example, I've made. For example, you can you can create these diagrams. Right? There's not much functionality here. You just can create blocks like this. You can delete them, and you can like put some wires arbitrarily like this. It's not very fancy, but then you can copy the diagram corresponding to it. Right? It's gonna create. Oh, this is like this diagram that I've been describing. So this is the diagram object as a network, right? It's like from the drawing, it parameterized these nodes with the corresponding like coordinates and position of the wires so that it looks the same, right? So I wonder if you can arrange it, what's going to happen. Yeah, there's going to be some ugly things happening. This basically means that there's some very heavy parameterization happening under the hood. So like all the ports being outputs and also some ugly names created. So maybe you don't want to do it. But obviously this is diagram. If you make it into a net graph, I guess. This is just graph now. So even you can tell it by the boundary. This magenta boundary means it's a diagram. Now it's an actual purple boundary means the graph. So this is a graph. You can turn it into a graphics if you want to. Now it's just a graphics object. you can modify this or vector graphics, or you can just draw on it if you want. Right. And so I'm not sure what can I say in addition to that. In a way, yeah, you can at least you can draw them and create graphics.
That's interesting. Was it hard to put that in?
The drawing widget,
Yeah.
or what?
Yeah.
Oh, this one is not very. It's not very complicated, I think. It's like we also have something like in the hypergraph. That was what was more complicated. It's related to it. Had this similar functionality of drawing hypergraphs. This one is more trickier, but basically, yeah, because I already knew how to create this kind of things. This one was easy. This is just like a very simple version of it. So you can make this hypergraph and turn it to a diagram. So there's like some functionality of going back and forth. So in a way, hypergraphs are interpreted as each hyperedge is a node. Yeah, this is like a spider.
So to diagram is a part of the hypergraph package or of the
No,
no.
part of this package.
And what is this package? How can I load it and test it? Is it already accessible somewhere?
Well, yeah, I can share this notebook, and it has this link here, so you can install it. It's technically part of Wolfram research, so, but I can share this packet here, like this. But maybe it's gonna end up on GitHub soon. It's just been very experimental. I'm gonna post this on Discord somewhere. Live streams. Of physics. Yeah.
So I did not get fully actually the debate about this closed compact categories. So what is the problem actually of implementing? What if when you were talking about this Pi machine, what is it what your package cannot do? I mean, there are some dual objects. So dual objects are in your diagram package are arrows which are input arrows but go out or something like this, right? Or
Yeah, those are like you can create, for example, you can create diagram technically, like make a empty diagram with a as an output, I guess, right? And you can shape it as a wire. Yes, you can do it, right? You can create diagrams like this. Maybe you can make it a dual. When you created just a diagram, there's no problem, right? Because this lacks any semantics. But when you want to interpret like loops like this semantically as a computation, you're gonna have a problem. You have like if you're gonna you have a type theory and you interpret the ports as types. What does it mean like for a function like eating an inverse type and like or whatever that means? Like as soon as you have a loop, there's no clear semantics how to interpret it and turn it into a function. So that's why Pi machine solves this problem of interpreting this inverse and negative types and actually specifying the whole machine and how you can run it.
So basically now if you cannot evaluate on this your diagram function, right? It would not bring
No,
anything.
I can't. No.
In the same way as if you had, for instance, like a diagram which would be a cyclic diagram, which would be just a circle, then you also would not get anything because it would be some sort of trace or something like this, right?
Yeah.
And
Well, you can make you can make a tensor. Like tensor semantics is clear for the compact closed categories. You can make traces and dot products or whatever you want. But the function semantics, computation semantics is less clear. Yeah. It's even less clear what like the logic semantics of it, or maybe not. It's like because in that Rosetta Stone paper, there's also the logic in the title, right? So in the physics, we have Hilbert spaces as types. In computation, we have just types of your values, and the logic you have propositions. And what does it mean, like, to have this kind of loops in the logic case? I'm not even sure. So, though, given that you have a much more clear correspondence between computation and logic with all this Curry-Harvard correspondence and all that, maybe it's much more clear. As soon as you have types, you basically have logic. So maybe as soon as you understand how computation works, you basically should understand how logic works.
And so they solve it by kind of how do they solve it in the paper, or what is the main characteristic of the
Well, they
pi
just
machine?
create all this way, just describe all the way you can run this machine, like what is the state is, like you have to, like, the state would gonna contain this continuation passing style, like basically a continuation, so that you can use it as a, in order to return to some previous computation. That's where you can implement backtracking more directly into it. But as soon as you specify all the semantics, all the rules, which is going to be painful to implement, maybe I should try LLM or something, to implement all of the semantics into some language and then be able to run it. Yeah, but I would like to see how this actual machine runs, so that you can make this correspondence, because when you run this machine in the usual way, when you have all these events explicit, all the updating events of the state, you can make this causal graphs and all the usual Wolfram physics types of things. When you turn this running of this machine into computation and see it from this perspective. So you make this space-time from running this machine, even though, because it under the hood it implements these backtracking events. In a way, it's quantum computation, even though they have a space-time as a partial events created from it. I don't know whether it makes sense. I guess I have to implement it first in order to explain it more nice. Well, if someone wants to help me to implement it, I would take that. It's like a community challenge. Implement the Pi machine, the Wolfram language.
You post this paper to the Discord?
Yeah. This bot is just okay.
Fine.
Why is it called pi machine?
I'm not sure, and it's not just this paper. I think it's just kind of the same authors build up this machine. There's some earlier works when you just have this universal reversible machine, which they call Pi machine, but then there are many papers that try to augment it in a different ways, like adding more types or adding some other weird semantics into it. But though you have this base Pi machine, which is just, you can just specify it, like this is everything you have to know of the Pi machine itself. It's like a, there's like a, when you want to formally describe like something like a lambda calculus, you just specify some variables, your abstraction, and the application of lambda terms and other terms to itself. This is like similarly, it's a bit more complicated. You have some formal definition of the things you can do in the language, and the way you specify it, it's obviously reversible, right? So that's the basic. This is like, this is some you can have summation types, product types, which are associative and commutative. Have some absorption thing happening, distributive things. Yeah, this is just the usual composition. Given this morphisms to functions from A to B and B to C, you can compose them to make a new function. This is just a product, sum of those, and the product of those. So the Pi machine itself is very basic, right? But the actual semantics, how to run it, like what kind of This is like some rules you can add. This is so you can, for example, you can implement this rule in the Wolfram language, right? Call it, instead of delta, you can call it step, right? What happens if you apply swap to this thing? So it should produce this thing. So just like a usual definition, rules you can program, right? And then you can also create a state with this continuation explicitly.
So
That-
why are these compact? What makes them compact? What's the definition?
Well, compact means that you have these units and co-units, which is just those exact U-turns, right? The U-turns that can be semantically interpreted. And basically, in PyMachine, they interpret it as when you have this U-turn, basically inverse type, multiplicative inverse type is the space is like a garbage collector. So it kind of eats the type, right? And the negative type, this is like a backwards computation, so it's backtracking. So they have the different semantics. So in a way, this two bimonoidal structure, when you have sums and products, they also have the different semantical interpretation as time and space. So it's also quite interesting. So in a way that you reverse the negative type is like going backwards in time, and the inverse type is like garbage collecting some things in space. With this I did.
So when the result of implementing this is going to be what? So what you are going to be able to do with it?
Well, I want just like basic implement all of these rules in the Wolfram language as actual rules, or just as definitions, and create these terms, some complicated terms. Like they have the most complicated example, they actually have like a SAT machine, SAT solver, right? So that you can like create some expression corresponding to a SAT problem, run eval on it, and it's gonna do all the computation on the hood with backtracking and garbage collected with all the semantics specified working. I guess that's the end goal here, right? But if you want to just this version have in the Wolfram language implemented, just play around it with all the reversible properties of that machine. Like what does it mean to run it in reverse even? Try to make it explicitly non-deterministic instead of explicit typing. I know. I just find it interesting. I just want to play around it with this idea a lot.
Cool.
It's like conventionally, this kind of machines are not implemented in the Wolfram language. You have to like do. They did it in Agda, which is like this. Yeah, they have Agda code, just very fancy Haskell basically, which are much more general types. That's why they chose it, I guess. But because Wolfram language doesn't even have types, it's a bit trickier. But I guess it doesn't matter because all you're actually manipulating is just some states and terms with some rules. So we just formulate it by the conventional rewriting rules, and that's it. It's gonna work. We don't have to be rigorous in order to have the types and some type checking capabilities. We don't care about those. We just want to run this for now. Yeah, and at the end, when you have this PyMachine, maybe it's going to be like a separate packlet, just a way of creating PyMachines, evaluating them. Then you can make a version of this diagram function that turns these arbitrary diagrams to functions, I can also make some diagram pi machine, which turns an arbitrary diagram with all this composed nodes together and ports into this pi machine that I can run, right? And also going back and forth, like from pi machine to diagram, just visualize the actual code. Maybe there's going to be a nice way to writing those pi machines as like some kind of domain-specific language. I'm just encoding some program with all of those types. I can run it, and then I can make just visualize it as a diagram with all this arrows going backwards explicitly. Let's see what in order to just examine it. Yeah, I know. See, they even use this quantum computation gates explicitly, like but in the context of this pi machine. So like you're not manipulating state vectors or tensors. You're manipulating some just classical types. But you can basically do the same things like quantum computers do.
What? So this can implement quantum gates?
Well, not as I said. So you're not explicitly making state vectors. So it's like you're not manipulating amplitudes or probabilities by multiplying them together as matrices and all that in Hilbert space. But you semantically you can perform the same kind of computation using these machines. And they have some other papers like actually making it more explicit instead of in a different way without these types of types, with inverse types and negative types. They have some different ways of turning the pi machine into quantum machine so that you can prove that it's universal quantum computer. So that you can implement any quantum gates using those. But those are not very interesting, I think, for well, at least to me. It's like this way of having inverse and inverse types are more interesting than just directly trying to make some versions of pi machine with maybe some rotated semantics or whatever they're doing. It's kind of it seems a little bit contrived. It's just trying to shove the quantum features directly instead of having them emergent. And I think they're going to be emergent with this with the inverse and negative types. You don't have to put some complex numbers explicitly into the definition of the machine.
Very cool. Very cool.
Yeah. So I guess we should
Wrap it up. Let's wrap up. So
there's no further questions.
Yeah, look forward to exploring this more on Discord and maybe sometime like open it up or in the GitHub for collaboration.
Could you maybe also share the link to the paper? You said that they are having a paper where they are relating it to some universal quantum computer.
Well, it's basically the same offers, maybe some of them. It's something like a pi machine. Let's see. Let me find it. How to bake a quantum pie. You can Google it like that. There are two papers. I think I've seen two papers, different ways of making quantum versions of this. Yeah, how to bake a quantum pie is one. I'm gonna just
And what I'm not getting, how are some quantum effects emerging from Pi machine? So what you are claiming that, so how one can see kind of this connection to it?
Well, if you think of those dual types, like those backtracking wires as antiparticles, and you can also interpret the antiparticles as some backwards retrocausal effects, right? Those can be, those are essentially like equivalent to usual Hilbert space formulation of quantum theory, right? Instead of having unitary transformations of your density matrices, you can have as soon as you like have these axioms of have some backwards effects, retrocausal effects happening. It's like I have a probability from the probability perspective. It's like having, I don't know. I don't know whether you've seen like me trying to explain like all this quasi-probabilistic interpretations of quantum theory. I think in there it's most clear what does it mean. So because you can interpret all of these Hilbert spaces instead of thinking of all the complex numbers and rotations in this complex space, you can just think of a quasi-probabilistic space when you just deal with probabilities, but in a forward and backwards directions explicitly. So in a way, you're performing some inference on your probability distributions, and this is going to be equivalent to a Hilbert space, right? So and in the quantum field theory perspective, you also have antiparticles, right? And in a way, they also had this weird nature, as though it seems like as though they going backwards in time, right? They traverse in space-time backwards. So as soon as you interpret in this way, and having this retrocausal effect, you can recover all the usual Hilbert space formulation, right? So as soon as you have this way of backtracking of your, if you implement basically antiparticles in your classical computer, you can have quantum computation effects, even though they're not going to be as efficient, of course, because you have to have this backtracking explicitly. But though quantum computers presumably doing it for you as a single step.
All right. So let's close it out. Thank you so much, Nick, for presenting and doing some live science. And thank you everyone on the Discord for tuning in the live stream. So we'll see you again next time.
See you next time. Bye, everyone.